All right. Hello, everybody. Welcome to tonight's event. My name is Kylie Kozlik. I am going to be your host and moderator for this evening. And as I said, welcome. I'm the program manager here at the Chicago Council on Science and Technology. And tonight's program, Every Breath You Take, Human Impacts on Air Quality, is all a part of the Chicago Council on Science and Technology's Climate, Energy, and the Environment program. This program is funded by the Baum Family Foundation. So we just wanted to shout out them and say thank you for creating an awesome program series. If you are new to C2ST, our mission is to inspire and engage all segments of society about science, technology, and their impacts on society. We're delighted to be entering our 17th year of offering science and technology programs, such as this one, to the general public. A couple housekeeping things as we get going. To ask questions, visit menti.com and enter the code 64354750. At the end of our presentation, we'll be answering questions from there. Our staff will also be checking the comments on YouTube and Facebook, so you are also welcome to ask questions there directly. Or as I said, go to menti.com and enter that code 64354750. If you want to learn more about C2ST, our upcoming programs, and even donate, go to c2st.org and you can learn more. So for today's event, I have the pleasure of announcing two speakers for tonight. We have Aryiana Moore and Dr. Daniel Horton. So Aryiana C Moore is a fourth-year PhD candidate in the School of Civil and Environmental Engineering at Georgia Institute of Technology. Her current research projects focus on freight-related air quality impacts in Los Angeles and air quality impacts of Hartsfield-Jackson Atlanta International Airport. Also joining us tonight, we have Dr. Daniel Horton. He is an associate professor of Earth and Planetary Sciences at Northwestern University. He is an Earth system scientist who studies Earth's atmosphere and climate and their interaction with people, places, and things. So we're super excited to have these two awesome experts here. First off, they're each going to share a little bit about some of their research and findings related to air quality. And then, as I mentioned, we'll jump into questions. So I believe up first, we have Aryiana, so take it away.
Thank you so much, Kylie. Could you bring up my slides, please? So today I've titled my presentation, Must Be Something in the Air. It's an introduction to air quality measurements and their uses. A little bit about me, even though that was a great introduction. I just wanted to say, yes, I'm a fourth-year PhD student, but more importantly, why do I study air quality? What does it mean to me? Well, first off, it's one of the elements of environmental engineering and environmental health that really impacts us every day. And because of that, I actually get to work with communities and with stakeholders on what their current problems are. So not only am I doing work that's impactful, but I'm doing work that's really up to date on the science. And then lastly, it gives me so many opportunities to do educational and outreach programs just like this, which I really enjoy doing. So an overview of what I'll be talking about today. First, I'll give an introduction to ozone pollution and how it's formed. Then I'll talk about how we estimate pollution in general in the air. And lastly, I'll talk about how we use air quality measurements in research, and I'll give examples using warehouses and then the Atlanta airport. So first off, in 2024, Chicago was ranked number 17 for high ozone pollution days in the metropolitan area. That same report showed that 40% of Americans live in places that have unhealthy ozone or PM 2.5 episodes in stand. The figure to the left is actually from the State of the Air report for Chicago. And essentially the thing I wanted to point out is that most of the counties in Chicago actually were rated an F based on those high ozone pollution days. The reason why we really care about ozone and ozone exposure is because it's been linked to a number of things, including acute respiratory distress, increased risk of respiratory infections, decreased birth weight and lung function in newborns when they're exposed to it in utero, and then worsening of already existing chronic respiratory illnesses. And sometimes that can even lead to cardiovascular or pulmonary related death. But let's talk about how ozone is actually formed. So ozone is what we call a secondary pollutant, which means that ozone is always formed in the atmosphere and is not emitted from some direct source. So it's not like you can turn off a source of ozone. Instead, we have emissions of things called VOCs, or volatile organic compounds, and NOx, which is NO and NO2, and they actually combine in the atmosphere when there's sufficient sunlight out to create ozone. So first, it's important to talk about emissions and how we often study emissions to think about air quality and to think about ozone formation. So volatile organic compounds include both biogenic sources, so sources that come from plants, as well as anthropogenic sources, which come from humans. An example of sources that come from plants are pinene and limonene, which pinene is the smell that we associate with pine trees or pine sol, and limonene is the smell that we associate with lemons. Whereas a anthropogenic or human source of VOCs and NOx emissions could come from cars, and cars and energy production are the top anthropogenic sources of NOx. So now, how do we actually estimate air pollution? There are two primary ways. We can either do this through models or through measurements and observations. I'll primarily be focusing on talking about measurements and observations. And there are two types of measurements or observations that we use for estimating air pollution. The first is we do in situ measurements. So the picture on the left is an in situ monitoring site that I have set up in Atlanta. And in situ measurements are measurements that are actually taken by pulling air inside of an instrument and measuring some property of the air to determine a concentration of whatever the specific pollutants you're looking at. So here, when I say instrument, I really just mean something we use to measure a property of something else. So for example, you would say an instrument of temperature is a thermometer, because a thermometer is used to measure temperature. So here, these instruments, as you can see, the white tubing in these instruments are for pulling air from the outside, and we have pumps that pull that air through the instrument. The pro of these types of instruments are that there's a wide availability of a number of in situ instruments that allow us to measure a large number of compounds that are relevant to the air. But a con is that it has low spatial coverage, which means that because you have to actually pull the air that you want to measure inside of the instrument, these measuring sites sometimes can only account for the air quality in a specific location where they're placed. And so low spatial coverage just means that they aren't covering a lot of space in an area. Alternatively, we have remote measurements. And the difference with remote measurements is that these measurements are taken of air at some distance away from the actual monitor. So you don't actually have to pull in the air into the monitor, into the instrument in order to measure it. The pro of this is that you get high spatial coverage. One of the most common examples of remote instruments are satellites. So I have the schematic to the left of the Tempo satellite. And Tempo was the most recently launched satellite. It was launched last year. And so these are actually up-to-date measurements from August 26th. And as you can see, Tempo scans the entire continental United States, which is just something we could never do with in situ monitors. So the pro of them is that they have these really high spatial coverage, but the con is that they're far more uncertain or less likely to be precisely correct than measurements that we take with in situ monitors. And then because satellites measure from the satellite instrument all the way down to the ground and give you a total concentration, that doesn't necessarily mean that it's relevant or correct for ground measurements and for surface concentrations. Because we often think of air quality as associated with health, we really care about the air near the ground that we breathe and may not care about concentrations of species further up, depending on what research question you're asking. So now let's go into some examples of using air quality measurements in research. So first, warehouses have become an increasing air quality concern in metropolitan areas. The map of the US to the left shows warehouses per 100,000 population, and this is per county. And so if you notice, the areas that often have the darkest color, which means that they have the highest warehouses per capita, are ones that are near metropolitan areas. So thinking of Atlanta, Los Angeles, and in this case, and even Chicago. And then the figures to the right are just showing a time series of how new warehouses are being built and then how their building area is getting larger. And essentially, starting around 2010, we really see this increase in not only the number of warehouses being built every year, but also in their sizes. So we're getting larger building areas. So one thing that Kerr et al., which is a researcher and research group at George Washington University, did was they used 2021 satellite data, so again, this remote monitoring instrument, to show that nationally, warehouses are associated with increased NO2. So the figure to the left, the white dot in the middle represents a warehouse, and upwind, or to the left of the dot, are the concentrations that are upwind of the actual warehouse, versus downwind or to the right are the concentrations that are downwind of the warehouse. Comparing upwind to downwind satellite data, they found that warehouses are associated with a 17.9% increase in NO2 on average across the United States. They also found that these enhancements, or these times where the downwind concentration of NO2 is larger than the upwind concentration, were even greater when there are a number of warehouses that were clustered together as opposed to warehouses that were spread more apart. But this brought my research group to the question of, they saw this on a national scale, but can we see it on the local scale? So we use summer satellite NO2 to identify hotspots, which are just areas of higher NO2 concentrations than the rest, in Los Angeles. And we found 3. So the first one is the most to the left, and it's downtown Los Angeles. Then in the middle, we find what we are calling a near warehouse hotspot. And then furthest right, we find that over downtown San Bernardino, there's a hotspot. So we identify this near warehouse hotspot, which actually is located over a small community that in recent years has sued the Attorney General of California over warehouse construction in the area, because there are just so many warehouses in this warehouse dense area. It's a place where people live, and specifically, there are a lot of warehouses that are within 1 mile of a local high school. But there's a question that just because these warehouses are near a hotspot doesn't mean they necessarily cause it, especially considering that, as you may notice, these warehouses are individual dots on the map, are often located along highways. And as we said, vehicles are a source of NOx. So we need to ask the question of, does this near warehouse hotspot represent the effect of warehouses, or is it really just an effect from typical highway traffic? So in order to answer this question, we modeled NO2 in Los Angeles without any overt emissions from warehouses. We kept emissions from total traffic, or from the highways. And so the results were analyzed for years 2018 to 2021. And in general, our modeled NO2 matched the satellite NO2 and were highly correlated. However, even though they were highly correlated, which means that as when NO2 in the model went up, NO2 in the satellite data went up, they had a difference between them. And so in order to quantify this difference, we used the normalized mean bias. And we said that for grid cells with warehouses, the normalized mean bias was often more negative, meaning that the difference between the model and the satellite was even greater than for normalized mean bias of the entire domain. Here's an example from 2018. So splitting the data into summer months and then peak shopping season, which I consider October to January, and sort of represents when we would expect warehouses to have the most activity year round. In the summer, for the overall data set, the entire domain, the normalized mean bias between the model and the satellite was 9.3%, negative 9.3%. However, when we only looked at grid cells that had warehouses over 100,000 square feet, we found that this normalized mean bias almost doubled. And when we looked at warehouses over 400,000 square feet, it was even greater, though not double. And we see the same thing for our peak shopping season, that overall for the entire domain is negative 9.1%, but that for the warehouses over 100,000 square feet and warehouses over 400,000 square feet, we become more negative in our model compared to our satellite, just meaning that our model is underestimating the amount of NO2 that we actually see from the satellite, even more when we're looking at these areas over the warehouse. And this means that overall, because this held true for most of the years in our study, the results suggest that warehouses have some unaccounted for impact on air quality, and specifically on NO2, that's greater than just the highway traffic. And so those were examples for warehouses. Now we'll move on to examples with the Atlanta airport. So first, it's important to know that Hartsfield-Jackson Atlanta International Airport is actually the busiest airport in the world, according to passenger volume. And that's been true since 1998, almost continuously, with the only year they came in second being 2020 during COVID. And so although we know that airports are a known source of air pollution, a lot is still really unknown about the total impact of airports on air quality. And one reason is because airports have vehicle emissions from vehicles actually on the ground. They have emissions from the airport terminals itself, And then they have airplane emissions, which are especially interesting because airplanes emit at the ground whenever they're driving. They're aloft during takeoff, landing, and cruising. And during cruising specifically, it's not just over the Atlanta airport, it's wherever distance that they're traveling. Relative to 2015, aircraft NOx emissions are anticipated to rise up to 300% by 2045, just as we're continuing this increase in demand for air travel. So even though we intuitively know that airplanes emit on the ground and in the sky, traditionally when we model airports, we assume that all emissions happen at the ground. A former colleague of mine, PhD student at the time, now a professor at University of Connecticut, Abby Lawal, decided to take this challenge on and created a 3D emissions model for the Atlanta airport, which included these airplane cruise emissions. And the results of that for NO2 are to the right. And I've circled the Atlanta airport. As you'll see, the Atlanta airport is right at the center of these increased NO2 concentrations under this 3D model. However, anytime that you're running a model, it's very important to do what we call validating the model, which means that you're checking to make sure that it has some connection to the real world. In order to do this, what she did was she said on the left, she ran a model using traditional emissions that are just on the ground. And then on the right, she ran her 3D model. And she said that if she compares it to satellite data, which then can cover that large area, it should be that her 3D emissions model better reflect reality according to the satellite data. And so how she looked at this is she said it's the satellite concentration minus the modeled concentration. And so for the figure on the left, the red area is where the traditional emissions are underestimating the airport area. And as you can see, that is why it's a darker color than the 3D emissions. So she was able to show that her 3D emissions were more effective in their modeling of the Atlanta area for NO2. Then based on that updated 3D model, she actually showed increases in ozone up to 4% across metropolitan Atlanta. So again, by using measurements, she was able to validate her model and then use that model to look at pollution that we weren't measuring. And then most recently, the Kaiser Lab has been monitoring air quality in a community near the airport. And the motivation for this is that we want to better understand how airport emissions affect local air quality, local air chemistry, and then potentially health. And so our preliminary results, which are included to the right, show that there are elevated NOx, both NO and NO2 concentrations, when wind is blowing from the airport toward our measurement site, which is the line in red, compared to when wind is blowing any other direction, which is the line in black. For our data, we've included from noon to 8 p.m. And this just kind of give an idea of the types of things that we're looking at. We're looking at how wind patterns affect concentrations because of the airport. And we're also even looking at how individual flights might be affecting air quality, or the number of flights in a specific hour might be affecting air quality. Lastly, what I hope you've learned is that one of the ways we estimate pollution is via measurements. These measurements can either be remote, which means that the monitor is separate in a separate location from whatever you're measuring, or in situ, and that measurements can be used in a number of ways. Hopefully, I've shown that they can be used to identify sources of pollution, to validate models, and then understand pollutant source effects on air quality. I would last like to acknowledge all the combined efforts of my peers in the Kaiser and Russell at Georgia Tech labs, and for those whose work is presented here. A special thanks to NASA HAYCAST for my research funding. And then lastly, of course, thanks to C2ST for inviting me to today's seminar. Thank you so much.
Thank you, Aryiana, for that wonderful presentation. I will take it away from here. I also wanted to thank Kylie and the rest of the folks at the Chicago Council for the invitation to present tonight. I will now start my presentation. All right, so we started off with a question, and the question was, can we reduce long-standing environmental injustices via EV adoption? And this is work that I've done with a number of different students and collaborators here at Northwestern and at other universities. And I wanted to give you a little bit of background on why we're asking this kind of question. And that background starts off with my background. I'm a climate scientist. I'm interested in human-caused climate change, and human-caused climate change is caused by increases in greenhouse gases in Earth's atmosphere. And climate science is at a state in time, and this is my own cartoon depiction of where we're at, where we understand the physics and chemistry of climate change to a degree where our advances, while they're still happening, we know enough about them that we can write down equations and model them in a computer and make predictions. We know that these climate change we know that climate change causes impacts to people, places, and things, and our understanding and advances in that realm has increased significantly through time, and now is starting to taper off a little bit. And I think where the real action is at this moment is investigating solutions to climate change. So we know climate change is happening. We know it's causing impacts to people, places, and things. So now let's focus our attention on solving this problem. And that's where my group's research comes in. And I'm particularly interested in a class of solutions that have co-benefits. And so these are things that actions that if we took them would both reduce the amount of greenhouse gases in the atmosphere, but also have benefits. And in the case of what we're going to talk about today, they have health benefits. And specifically, we're talking about transport. And in the US, the total greenhouse gas emissions from the transportation sector are approximately 29% of the pie, so the largest sector contributing to greenhouse gases. So eliminating those greenhouse gases would be highly beneficial to the climate system. At the same time, if we eliminate the tailpipe emissions that cause greenhouse gases, we'll also eliminate lots of the air pollutant emissions that come out of tailpipes. And air pollutants that come out of tailpipes have lots of negative health impacts, anything from resulting in low birth weights all the way up to premature mortality. And so this kind of motivates our research question about electric vehicle adoption. The other piece that motivates our specific research comes from the Justice 40 initiative. And this was a Biden and Harris initiative that occurred when they first took office that suggested that they were hoping to have 40% of federal investment benefits going to disadvantaged communities. And so this definition of the various words in this sentence are very debated, and we're not going to get into all of that. But to be able to decide which communities are disadvantaged and how they're disadvantaged, we need a lot of information at very high resolutions across those communities. And so from an air quality perspective, this creates the need to characterize air quality in urban environments. And urban environments have very steep pollutant gradients, meaning pollution changes from one place to another very quickly. They also have steep demographic gradients and health gradients. And so these are all things that we can investigate as scientists. And if you know anything about Chicago, you know that it is an incredibly diverse city. But if we're interested in understanding where air quality is good and bad in our city, the gold standard tool that we can use are surface monitors, as Aryiana informed you. But if we look at the map on the right-hand side, you'll note that we don't have a lot of monitors in the city of Chicago, which presents a huge problem for us to identify neighborhood-to-neighborhood variability in air pollution. And so instead, we can turn to physics and chemistry-based mathematical models to simulate air quality over a city like Chicago. And so my group has spent the past several years trying to get good at doing this. And our first effort was led by Anastasia Montgomery, who I believe presented for C2ST just a couple of years ago. So her work was basically taking an EPA regulatory model, a model that we call WRF-CMAQ, and applying it over our region. And this model is incredibly complex. It includes all sorts of factors that are important for determining air quality. It includes things like the emissions of pollutants from both human sources and natural sources. It includes meteorology, and it includes all sorts of atmospheric chemistry that can form things like ozone, which is a secondary pollutant. And so with this model, we run simulations that are time evolving, and they look like this animation that you're seeing. The first thing you'll know about this animation, or notice about this animation, is that it's very pretty. It's a lovely purple color, and it's showing beautiful wisp of cloud-like features moving across our region. This is Southern Lake Michigan, if you're not familiar. What you're really looking at here is ozone concentrations at the surface level, and these are every hour of our simulation. The little dots across the screen are places where we have ground measurements. And then if you look down at the bottom, you can see kind of the humps, and that's the diurnal variability of increasing ozone concentrations and decreasing ozone concentrations that fluctuate with the time of day, because ozone grows with sunlight, and then when there's no longer sunlight, you're no longer making ozone. You're also seeing the little dots dancing up and down on the one-to-one line, and this is our comparison of observations with the model simulations. And so this is one of the ways that we validate a model like this. So not only are these models really good at making pretty graphics, but they also can tell us things about where we live and how our air pollution, how good our air quality is. Okay, so with that model, we create estimates of air quality over a large region. You can see the region that we simulate in our model here. These simulations are run at 1.3 kilometers, which is pretty tiny when it comes to chemical transport modeling. What you'll notice in these diagrams right off the bat is that most of the action in this part of the world is occurring in Chicago. So we can zoom in there. And what I'm showing you is 3 different pollutants, EPA criteria pollutants. On the top, you're looking at NO2, or nitrogen dioxide. In the middle is ozone. And at the bottom is particulate matter, which is kind of exactly what it sounds like. It's little dust-like fragments that are floating around in the air that come from both natural and human sources. And if you take this perspective, what you'll notice is that, at least from an NO2, or a nitrogen dioxide perspective, and a particulate matter perspective, most of the pollution in Chicago falls along highways. Most of the higher levels of pollution, I should say. You will notice that there's an inverse relationship between where ozone is high and where nitrogen dioxide is high, and that's an interesting atmospheric chemistry fiat. But the majority of what I'll talk about today we'll be talking about the nitrogen dioxide concentrations. What a plot like this shows us is that if we think about transportation, transportation is a great way, if we eliminate tailpipe emissions, to have a profound positive impact. All right, so what we can do with those plots of pollutants across Chicago is map them onto census tracts, and that's what we've done here in the top row. Same pollutants, they're just depicted over census tracts in Chicago. That's helpful because with that information, we can overlay the various demographics of populations that live in Chicago. And if you look at the bottom plots, you can see that done for race and ethnicity. And the thing you'll notice here is that, and it probably won't be a surprise to you, but Chicago is an incredibly segregated city. Populations of one race and ethnicity are quite high, where others are quite low. And so that's a challenge when it comes to creating solutions to poor air quality. And here's kind of an example of that laid out. On the right-hand side, you're looking at relatively high exposure levels to various pollutants broken up by incomes and race and ethnicity. And the primary takeaway of this plot is that if you're on the right-hand side of this plot, it means you are exposed to a greater amount of a particular pollutant. And if you're on the left-hand side, you're exposed to a lesser amount. And what you can see is that there is no individual community or income group that doesn't see some level of negative consequences of air pollution exposure. And that's one of the challenges of designing effective solutions to poor air quality. All right, now that we have kind of the lay of the land and we know that we have a model that can simulate air quality over Chicago, we can get to the heart of our question, and that's vehicle electrification and what effects that will have on exposure, on population health, and also on environmental justice concerns. And so we ask all of those questions using this same exact model that we used previously, the WRF-CMAQ model. And in this case, because we're simulating electric vehicles, we have to take into account two changes in emission sources. The first, and it's depicted on the left-hand side, is changes in tailpipe emissions. And so naturally, if you're reducing tailpipe emissions because you're electrifying a battery or electrifying a car using a battery, the majority of the emissions decreases will occur along roadways. And so essentially you're looking at a map of roadways here, and this is a reduction in NOx pollution or NOx emissions when we electrify 30% of vehicles on the road. The other thing that will need to change in the emissions framework is that emissions at power plants will increase. And this is emissions at fossil fuel combustion locations. And so we're able to map the energy demand for a 30% transition to electric vehicles and map that onto power plants and then simulate the increase in emissions that come from those power plants. And so we're weighing the balance between decreases in emissions that are on road versus increases in emissions that are at power plants. And that's what we simulate. And we simulate that in our WRF-CMAQ model. And this is work that was done by an undergraduate that was working in my laboratory for approximately 3.5 years. And he published this study this past year where he simulates, again, 30% of all vehicle types. And what do I mean by all vehicle types? Well, it's everything in this picture here, everything from tractor trailers all the way down to motorcycles. And what you'll note is on the two outside plots, you're looking at the change in concentration of nitrogen dioxide on the left and particulate matter on the right. And you'll see that those concentrations are decreasing. In the middle, you're actually seeing increases in ozone concentrations with the adoption of electric vehicles. And this is something that happens because of a reduction in NOx pollution. And it turns out that NOx helps destroy ozone. And so a little bit more NOx will form when we electrify vehicles. All right, so what do these changes in concentrations mean to people's health? Well, there's lots of ways that air pollution influences people's health. It can result in asthma. It can decline or degrade cognitive abilities. But by far the most impactful is premature death. And so we use epidemiological functions to look at changes in concentrations of pollutants and people's exposure to those pollutants to determine changes in premature death in each census tract. And so the gist is that when pollution decreases, we see a decrease in premature mortality. And so again, the two plots on the outside have reductions or fewer deaths each year because of decreases in pollution. The largest impact is because of that decrease in nitrogen dioxide. It's up to 1,120 fewer deaths per year because of that decrease. And again, in the middle, you'll see a slight increase in deaths, and that's because of increases in ozone concentrations. Now, one of the things that we noticed when we did our initial study was that the majority of the impact was from heavy-duty vehicles. And so we also did another study where we only electrified heavy-duty vehicles. And so we're talking about motorhomes, buses, garbage trucks, tractor trailers, that kind of thing. And in this case, I'm zooming in again on Chicago, and we're going to focus exclusively on nitrogen dioxide concentrations. What you'll note is that in the blue colored plot, you're seeing the decrease in NO2, and this is again over census tracts. It mostly tracks along highways where it's maximum. And to determine where mortality changes the most, we have to combine our change in pollution concentration information with information about the susceptibility of the populations that live in those census tracts. And to do that, we use what are called mortality rates. Combining mortality rates or susceptibility with changes in concentrations gives us our change in nitrogen dioxide attributable mortality rates. And so all summed together, what you can notice in this plot is that mortality decreases do not necessarily overlap substantially with where nitrogen dioxide decreases the most. And this is a quite interesting finding. It suggests that certain populations are more predisposed to being impacted by poor pollution. And that susceptibility, that higher susceptibility to poor air quality, is something that can be driven by lack of access to healthcare or lack of access to healthcare that is non-racist, so on and so forth. And so these are some very interesting findings that we had. And what we did is then plot them according to their rank across the city, and then examine where exposure decreased by race and ethnicity, and also where health benefits were the largest according to race and ethnicity. And what we found was that the pattern of nitrogen dioxide exposure reduction differed from mortality reductions, and that the health benefits were disproportionately large among the Black populations within Chicago. And that is largely driven by higher levels of susceptibilities in those communities, driven by lack of access to healthcare and other factors that are related to systematic racism and redlining. And so a summary of this investigation of one solution to both climate change and poor air quality is that EVs are both a net positive for greenhouse gases and air pollution. I didn't really talk about greenhouse gases that much, but because it's a less of an interesting story, but greenhouse gases are reduced when we adopt EVs. Many of the benefits that we see occur in marginalized and disadvantaged communities. And I wanted to say thanks to the students and collaborators and funders that made all of this possible. And then just to summarize, it's a very practical thing to think about consuming, right? We all consume things. We all like things like Cheetos delivered to our convenience stores. And finding ways to do that in a responsible way, a way that doesn't impact people and certainly doesn't impact disadvantaged communities more than others, seems like a good thing. And so thanks for your attention. I'd be happy to take questions as we get into the questions portion of tonight.
Yeah, thank you both so much for kind of laying some groundwork for us. As you can see on the screen, if you have more questions, you can go to menti.com and enter code 64354750. It's on the bottom of the screen as well. And we're going to go through some of these questions. The other thing I will say, both Aryiana and Dan, if there are things related to the questions that you want to share, we can do that as well. But some of the questions that have already come in, this first one, some folks are curious, how does America compare to other countries in terms of air pollution? If you know.
So I can take the first crack at that. So one thing I think that is really important to stress is that the Clean Air Act is one of the most incredible success stories from a regulatory standpoint. Air quality in the US used to be much, much worse. And from the 1950s onward, we've made substantial progress in reducing the amount of air pollution that we experience. Compared to some other places, we're doing much better in terms of air quality. So particularly developing nations like India and China have huge air quality problems. But we still have issues, and particularly, much of my research indicates that a lot of those issues persist in disadvantaged communities.
Thank you very much.
Yeah. And one thing I do want to talk about disadvantaged communities is that we both talked about metropolitan areas because a lot of the people live in metropolitan areas. But one thing that I've really trying to push for more is doing research in rural populations, because often the things that rural populations, especially in the US, but also in other countries, are concerned about, they're still concerned about their air quality, but the sources of their air quality change.
Yeah, there was actually a question from our audience, and it had some upvotes about the distribution of sensors. How does that change the data in cities versus rural areas? There seem to be more sensors in cities. There seems to be some interest about the city versus rural. Would you care to elaborate a little bit?
If you would mind, I think that that's one of the great things about satellites. So I talked about the Tempo satellite, which is specifically over North America, and it's able to get hourly during the day information across the whole continental US, parts of Mexico, and I believe most of Canada. And that's just something that, due to financial resources, could never be done on the ground. Like the number of researchers you would need, the number of instruments is just not really possible. And then there are orbiting satellites that orbit the whole world, and they orbit every part of the world once a day at a specific time of day. And we have multiple orbiting satellites. So we're kind of doing the best we can with the science, even though, yes, it is ideal that you have a surface monitor in an area near you. One of the reasons why people who control the data and validate the data of the satellites are doing so much research is because they want it to be as accurate as possible worldwide, so that's useful worldwide.
Very cool. That's super cool. And I know we'll share some of these, and they are on the website. But both Aryiana and Dan shared some resources that you can check out, including if you want to check out some of that Tempo data for yourself. So another question here, obviously, Dan, you mentioned electric vehicles or EVs, but what new technologies are going to have the biggest impact on improving air quality? And there's a follow-up question of how can we support, kind of as, not working scientists, right, that innovation in those areas?
Yeah, there's so EVs are something that I like to talk about because my research group is really interested in that question. There's something that maybe not the average consumer thinks about when they're going to buy a car, but certainly a large fraction of people are starting to think about them more and more. But there's other sectors of that have emissions that are out there, right? So there's agriculture, there's industry, things like that, and they all have emissions of some form that need to be dealt with. And so, from the perspective of something like an industry, something like the cement industry is a known major polluter when it comes to carbon dioxide emissions. And so finding innovative solutions to reduce the amount of CO2 emissions from cement creation is a really important topic, and it's one of the harder nuts to crack when it comes to mitigating those kinds of emissions. And there's a tremendous amount of research going on right now in terms of alternative forms of cement creation. In fact, even injecting CO2 into cement as a way to sequester some of that extra carbon dioxide that's created in the process of creating cement. That's one example that I can think of off the top of my head, but maybe Aryiana has some others.
So the example I immediately went to was forest fires. So perhaps we know that air quality is worse on times like right after the 4th of July when people are popping fireworks, or when certain activities that like individuals do. And so one thing I always tell people is to try not to start forest fires in your area. Obviously, there are a number of reasons why you don't want to do that. But even like people who burn like garbage outside of their houses, if you live in more rural communities, like even though that trash is no longer going to a landfill, perhaps the way that you're burning it is causing problems, especially in downwind areas. So even small things, small personal things like that you can do to affect your local air quality.
So this question comes from someone who has been checking out the purple air data. And so if whoever takes this one could also tell a little bit about what that is for the rest of our viewers, that there are a lot of sudden shifts in like particulate matter, especially like particulate matter 2.5. So they were curious what causes these kind of sudden changes and shifts.
Would you like to take that one?
I could take a swing at it, unless. Okay. All right. So Purple Air is a company that sells monitors that anybody can install at their house. And you often have the ability to connect that monitor to the internet and then share the data it's collecting so that everybody around your town or city can see what the reading is saying. It often pops up on social media that people are looking at Purple Air monitor, and particularly last year during the wildfire event, Purple Air data was all over the place because people were noticing that their air was not clean. And so these monitors are, they're not what I would call EPA grade monitors. They're low-cost sensors that are in some ways educational, but also informative. And so what that means is the EPA is not going to make a regulatory decision based on the data collected by these monitors, but they can be quite informative to us, the regular people that are concerned about air in one part of town. One of the huge benefits of having these kinds of monitors in places is that there just aren't that many EPA monitors in the country. And so these kind of fill that void. A number of cities are starting their own initiatives to have their own low-cost sensor networks across the city, but not every place has that. And so these Purple Air monitors can be quite valuable. Now, the fun thing about data and measuring environmental variables is that it can be noisy, but your instrument can also be noisy. And so when you see a temperature reading from, a weather station, that temperature reading is an average over a time period. So that data has been post-processed. And what you're seeing with the variation in the PM monitor, the Purple Air monitor, is it could be noise in the machine, or it could be, if it's going up when somebody is parked outside of your house, then you might have an actual signal. But it could just be noise in the machine. And that's something to be expected in instruments. And it's something that data analysts and scientists filter out by averaging over time, typically, when we have these kinds of sensor readings.
I think that was a great overview. I think the only two things that I would add is that the way that my lab kind of thinks of Purple Airs is you don't trust a single Purple Air, but you do trust a network of Purple Airs, not necessarily to give you an exact number. Like if it says there's 3 micrograms per cubic meters, maybe don't trust that exact number. But if it says there's 3 in one area and 10 in another area, you should be able to trust that the distribution of pollution is correct, that in that area where it says it's 10, it probably is higher than that area that it says it's 3. And then a personal story, I do put monitors out in locations that are research grade monitors. And I have found that sometimes you just unknowingly put your monitor near a source of pollution that you weren't expecting. And so I know of personal stories where people have put their purple air monitors or other personal low cost sensor monitor somewhere outside of their house, and happens to be that it was near like an exhaust vent or like Daniel said, near the, like, let's say parking garage near vehicles. Or if that person smokes, they put it on the same balcony that they smoke off of. And so because of that, they were almost always seeing really high values. And it worried them because they thought, oh, my air quality in my area might be really bad. But instead, the reality was just where they put the monitor was really close to a source. So that wasn't representing the air around them. It was representing the air right at that place.
Yeah, I think that's a really valuable insight of like the network, right, and kind of these averages over time as well. So this is a question more specifically about warehouses, and it asks, is there an alternate to warehouses that are more sustainable? If you have insights, I know some of the work is proving that warehouses cause problems, but yeah.
So there are a few different options that different stakeholders have put in. One of them is we don't need, and this is going to upset a few people, we don't need overnight shipping. We don't need one day shipping. Like, it is more sustainable to plan routes more according to how we do it for general mail routes, where it's not that we always have to have like a huge stock reserved near a city because the person who's ordering whatever that item is needs it immediately. And that can be the same for if you're thinking about like stocking Walmart. Like, Walmart can plan differently. Instead of being stocked every Tuesday, they can plan their stocks in accordance also with the Target across the street. And you're limiting the number of these heavy duty vehicles that have to go in between places, but also go to a place, keep their engine on. You know, some, especially during winter times in certain parts of the US, they don't turn their engines off for sometimes hours at a time. It's a lot of looking at small details like that of making the warehouse, I guess, more efficient. And then California in particular is looking into doing something unique, which is requiring heavy duty vehicles to switch to more environmentally friendly delivery trucks at the border. So they're thinking about making that a rule. But in order to make rules like that, you have to for sure know that there is a significant problem, because that interrupts with business as usual otherwise.
And then this is kind of a broader question, but how does having an understanding of air quality science affect your daily life? Do both of you have any tips for healthier or more sustainable living for us?
Oh, well, I have one off the top of my head. I tell it to everyone I know. So two things. If you are really into, to answer the question of like, how has it changed my life? I now understand the science of epidemiology in a way that I previously read papers about environmental health or on the subject because I wanted to stay informed, but I didn't really understand how much uncertainty goes into what the final results say, and why it really is necessary to have not just one report that says the air quality in a location is, let's say, unhealthy, or that there are environmental justice problems in one area, that it's really important to have multiple studies in an area. But then my advice, I have two things. The first one is, if you do 3D printing in your home, if you don't have a good exhaust system, I would highly suggest that you move your 3D printer to like a garage, or you create like an exhaust wind system like outside your window. There's a lot of early evidence that 3D printers release particles in the air that are really small, and that they can build up and stay in your house if you don't have good ventilation for long periods of time. And that's obviously something that is like new and upcoming research. But I think even some of the preliminary research is showing enough that I would be on the safe side and do that. And then because of COVID, air purifiers have become really popular. And I'll make sure to send it to C2ST. But there are a lot of air purifiers that have been put on the market that just simply don't work. And there are only a few labs. There are, thousands of air purifiers and only a few labs that are testing them. And so there's a verified list of air purifiers that show you that they work, and they explain in easy to understand consumer terms how well they work and what size rooms they should be in. And I can send that information for anyone who's interested in it.
Yeah, and I'll just add to that in terms of, I always say this when I talk about climate change and things that individuals can do, but we all consume and we all can vote at a certain age, and there are good decisions we can make with both of those relevant to the climate and air quality. And so my best advice there is to educate yourself and vote and consume accordingly. The other piece I'll mention is that, as I've gotten more and more into the world of air quality, as a professor, I get contacted about doing consulting gigs and things like that. And one of the ones I've gotten relatively frequently, and it's kind of attached to the style of research we've been doing, is from people that want to purchase homes and want to know where the better place to live in the city is. Almost to the level where, I could call up Zillow and say, we need to make an air quality map to overlay with the houses that are for sale in this particular city. And I don't, the science is just getting there, where we can say things about neighborhood by neighborhood in terms of where air quality is better or worse in a city. But there is some fairly obvious things about making decisions like that, such as, living near a highway is probably worse than living far away from a highway, and living near an industry is obviously worse than living further away. And so keeping those tips in mind as you get to the place where you want to purchase a home or live somewhere, that's one way that kind of surprised me, that getting into the world of air quality has affected what I think about on a regular basis.
Thank you both very much. In addition to, right, we've talked a lot about different air quality numbers, and you mentioned briefly, right, like over the course of the day, right, air quality or poor air quality gets worse, right? And then what other factors, we always hear about it more in the summer, right? Like what things cause these like big changes in air quality? Like when we had the heat wave 2 days ago, right? It was like also air quality.
Yeah, this is a fun question, and I feel like there's probably a lot of answers that we could give. But air quality is dynamic, and I for a long time in my career, I was really focused on just climate change impacts, and how I kind of segued into the world of air quality was thinking about the kind of meteorology that allowed poor air quality to form. And what does that mean? It means that there are certain times when the weather conditions are just right that pollutants can accumulate in the near surface environment. And so on a day-to-day basis, the weather has a huge influence on the concentration of pollution in a place. There is, of course, diurnal variability and atmospheric chemistry that Aryiana can probably speak better to than I. But yeah, meteorology has a huge influence on poor air quality. And a prime example is the difference between concentrations of ozone in the wintertime versus the summertime. And that's tied to the amount of sunlight that we get. Ozone requires sunlight to form. And so in the wintertime, there's far less sunlight, and so there's far less ozone in the wintertime.
Yes, so I'll say when people ask me like, oh, what impacts air quality, I normally think of it as like what inputs. And so the inputs are emissions. They are meteorological variables like temperature, how high the boundary layer is, because there's this idea that when we're mixing things in the atmosphere, it doesn't mix all the way to the top of Earth's atmosphere. What we're affected by is only some like amount at the surface, and it's capped off. And that cap changes depending on the time of day and depending on how hot it is and other things like that. And then there's also transport. So in some areas, you're going to have more wind than in other areas, as well as chemistry. So those are like the top 4 things. And what's so interesting, especially when you're thinking about modeling or when you're thinking about just looking at data, sometimes the initial gut impact, especially if you're like near a source, is to say that this source is causing bad air quality. But we've been able to show that actually it has nothing to do with that source. That source hasn't changed at all, and it's all meteorology. Or in other times between, let's say, 2020 and like 2010, we can show actually all of the changes between that is all emissions. And so it actually makes it fun from a research side, but complicated from if you're a stakeholder who just wants the easy answer of, I want better air quality, what do I do? We have no control over the meteorology. We only have control over the emissions. And not in every situation does just lowering emissions lower the concentration of air quality. So it is really a complex like question to answer.
Yeah. I think in response to your answers, we got a couple questions more specifically. How does rain affect air quality? If you all can elaborate. And there was also a couple of questions on like, does Lake Michigan or like being near like freshwater or saltwater have any effect?
So I can answer the rain question because it's one of my favorite things to tell people. Typically, rain makes what it was an air quality problem into a water quality problem. And what I mean by that is if there's particulate matter in the air, the rain literally washes it out of the system. So I always get to tell the other people in my building, because I'm an environmental engineer and we deal with the other suites, is that's not my problem anymore. That's your problem when it rains. So.
On the Lake Michigan side of the question, Lake Michigan is interesting because it provides a place with limited deposition, or what we call limited deposition. And so one of the ways we get ozone out of the air is that it gets deposited on surfaces on land, and often those are plants. Those plants have stomata and they breathe in air and they can suck in ozone and take it out of the air. Over Lake Michigan, that doesn't exist. And so often the pollutants in Chicago waft over the lake, and they can kind of sit there and bake in the sun and have very high levels of ozone. And when the lake breeze kicks in, some of that ozone can come back to shore. We see that happening over Chicago, but we also see very rural parts of Wisconsin with very high levels of ozone concentrations that are largely due to pollution that happens near Chicago, but gets blown over coastal Wisconsin. And then in terms of saltwater versus freshwater, one interesting thing about this is that sea spray results in evaporation and salt getting into the air. And that salt is an aerosol or a particulate. It's one of the particulates that make up particulate matter. The thing to know, though, is that when we talk about particulate matter, we're talking about a whole bunch of different stuff, all the way from things like sea spray to regular old dust to metals that are floating around in the atmosphere. And these things have different impacts on human health, and we call that their toxicity level. And so certainly something like salt from seawater has far less of an impact than something like a heavy metal that might be wafting around in the air.
Very cool. So we're getting close to time. So, we've talked about a lot of different things today. And I just wanted to give both of you kind of an opportunity to share any last things that you really want people to take away when they consider air quality. What are, say the one or two most important things that you'd like us to go home knowing?
So I could start, and it sort of ties back to the Clean Air Act. The Clean Air Act I believe, came into law in 1963. And like I said, it's been wildly successful in making air better for people to breathe. And the reason that it's been wildly successful is that it's been updated with new science on a regular basis. So basically, the science gets done, researchers like Aryiana and I do our work, and then at some point, that science is collated, codified, and turned into new regulations that become adopted as an amendment to the Clean Air Act. And so solving this problem is very doable. And we have a tremendously successful track record of achieving that success. And so what I'd say is that despite the amount of success we've made, there's still problems, but we are designing solutions and figuring out ways to solve even those harder nuts to crack as we move along. And so it's not like a hopeless situation. It's a very hopeful situation from my perspective.
Kind of piggybacking off of that, I would say, know that people care. I think especially in today's time, with how many environmental problems that there are, how many problems there are in the world, it may feel like there aren't people working on it and there aren't people who care about you and who don't care about whatever your family or the people you know and love are going through. And I just want to say, me and many of my colleagues we love meeting people whose problems that we can help and whose problems we can help solve. So it's know that even if you don't ever meet us, or even if you don't get to see us and see the work that we do, there are people all across the country and in other countries that are working on understanding air pollution, understanding how it affects people, and then understanding how to reduce it.
Thank you both very much. Thank you both so much for joining us today, sharing about the awesome work that's happening in your labs and in your research. It's been really exciting to hear. Thank you to everyone who submitted questions in the Menti as well. It's always helpful to answer questions from the folks who are listening. So if you're in the Menti, one other thing that we ask is give us some feedback about how this program went. If you go to the second slide or the second page of the Menti, there's a link just to a quick Google form so that you can tell us what you thought of the program. It just helps us make every program a little bit better. That being said as well, if you want to support more programs like this one, feel free to go to c2st.org. You can check out our future programs. You can donate. And you can sign up for our weekly newsletter, which is the best way to hear about all the cool things that we're doing. It's also where we will post things like the video of this talk when it goes live, right? So that you can know what's happening. And as always, you can thumbs up, you can like this video on YouTube, on Facebook, share it with your friends and family. We want as many people to know about all the cool things we talked about tonight as possible. And with that, thank you so much for watching and for joining us tonight. And thank you again to Aryiana and Dan.